In Rust, when you create a variable, you become its owner. You have the exclusive right to use and modify that variable. However, there are situations where you want to share that variable with another part of your code without transferring ownership. That's where borrowing comes in. Borrowing allows you to lend the variable to another part of your code temporarily. When you borrow a variable, you're saying, hey, I'm letting you use this variable, but I still want it back later. The borrowing system ensures that you can't modify or use the variable in conflicting ways while it's borrowed. Inside main, we create a new string. The string type in Rust is a dynamically allocated, mutable string. This string is owned by the variable myString. Then, we call the takesOwnership function and pass the string as an argument. This line transfers ownership of the string to the takesOwnership function. Ownership means that the function becomes responsible for the memory associated with the string. Inside the takesOwnership function, we print the value of the string, which is the own string passed as an argument. The function has complete control over the string and can modify or use it as needed. If we try to uncomment the print statement and print the value of the string after transferring ownership, the code will fail to compile. Rust's ownership rules prevent us from using a variable after it has been transferred to another owner, ensuring that we don't accidentally access invalid or deallocated memory. This example demonstrates how Rust's ownership system ensures memory safety by tracking the ownership of variables and preventing invalid memory accesses. In this code, we have made two changes. First, we modified the takesReference function to accept a reference to a string instead of owning the string itself. The function parameter is now a reference to the string, which indicates an immutable reference in this case. Now, the takesReference function receives a reference to the string and can use it within its scope. We print the value of the string, which represents the borrowed reference. After calling the function, we can still use string in the main function because we only borrowed it rather than transferring ownership. We can safely print its value without any compilation errors. By passing references instead of transferring ownership, we can share data without giving up control or incurring unnecessary memory allocations. Rust's borrowing system ensures that references are valid and the borrowed data is not modified in conflicting ways. In Rust, variables that have a type with a known size at compile time, such as primitive types like integers and booleans, don't need to be passed as references when used as function arguments. This is because these types are stored entirely on the stack, and their size is known at compile time. When you pass these types as function arguments directly, Rust performs a copy of the value, rather than transferring ownership or creating a reference. This is known as copy semantics. Copying the value doesn't have any additional runtime cost since the size is fixed and known.